Hello everyone and welcome back to MrMiers Math Channel. Today in Algebra 2AB, we're going to go over section 8.4, which is talking about logarithms and logarithmic functions. So our goal for today is going to be to evaluate logarithmic functions. And as always, we're going to have a short little practice worksheet afterward. So let's get started. So we're going to start with a place that we're familiar with. So we know that 3 squared equals 9. All right, and we also know that 3 to the third equals 27. Remember, that's just 3 times 3 times 3. However, for what value of x does 3 to the x power equals 18? So in other words, what would we have to raise 3 to get 18? Now, obviously, if we know 3 squared is 9 and 3 to the third is 27, it's got to be in between those two values, okay? So it's got to be some decimal or fraction in between 2 and 3. And instead of repeatedly, we could go through all the different iterations, and really it would only take about 27 tries to get, at maximum, to get to the nearest thousandth here to our answer. But we could go through a bunch of different iterations to figure out exactly, what it would be. But that would take a lot of time. So instead, to find the exact value, we define logarithms. All right, so I like to say essentially a logarithm undoes an exponent. Okay, everything has like an inverse operation. We've talked about this before. We've talked about squaring something and taking the square root, and how square root functions and quadratic functions, those are inverses. Same is true for our exponentials and our logarithms. So a logarithm basically just undoes an exponent. So to find that exact answer, we would take log what's called base 3 of 18. Okay, and this is where we're getting our 3 and 18, and we'll go over how we could rewrite this in logarithmic form. So that gives us 3 to the 2.631 is about 18. Okay, we're just rounding to the nearest thousandth there. All right, so this is how we could solve that original question, 3 to what power equals 18. We would use a logarithm. All right, so a logarithm with base 10 is actually called a common logarithm. It's denoted by log base 10 or simply by log. All right, when you look at your calculator and you look at the button that says log, all right, that is our common logarithm, log base 10. Okay? Now to figure out what all this means, we're going to go to the next step. Oops. Clicking on a bunch of stuff. There we go. Okay. So definition of logarithm with base b. Let's say b and y are positive numbers such that b isn't 1. The logarithm of y with base b is denoted by log base b of y. And it's defined as follows. So we could rewrite our logarithm as an exponent. So log base b of y, let's say that equals x. We could rewrite this and say b to the x power equals y. So just to clarify, let's throw in that last example there. 3 to the 2.631 was about approximately 18. All right, and to figure out that answer, we did log base 3 of 18, and that's how we got that 2.631. All right, so obviously these numbers are all interconnected, and we could rewrite this logarithm as an exponent, and vice versa, we could rewrite that exponent as a logarithm. One helpful way to rewrite logarithms and exponentials in that other form is by following the swirl method. Now the swirl method is really, really simple. There's nothing mathematical about it. All right, we just start at the first variable, b, and we're going to swirl our way around. All right, so we start with b, meaning we write down b first. Next thing that we would write down is x. Okay, we're just skipping right past y, and then we land at y. So that's b to the x equals y. All right, we could follow the swirl method to rewrite an exponential into a logarithmic. All right, so once again, we do the same thing. All right, we just swirl it. So that's log base b of y equals x. Obviously, this is a simple trick that we could use. Obviously, if we really understand what a logarithm and an exponent is, we don't need the swirl method. But the swirl method is really handy. All right, so b is the base of the exponent. X is the actual exponent, as we can see when it's in exponential form. And then y is what we call the argument. Okay, log base b of y equals x, and b to the x power equals y. All right, let's use this to rewrite some of these logarithms and exponents. So let's get to the next one. So we're going to rewrite the equation in exponential form. All right, so we have our logarithm, log base 3 of 81 equals 4. Now still, we really don't know what that means at this point. Let's rewrite it in exponential forms because we're a little bit more familiar with exponentials at this point than we are with logarithms. There we go. So we're going to use the swirl method. Start at 3, go to 4, come back to 81. All right, so start at 3, go to 4, come back to 81. All right, so this is something that we know. 3 to the 4th power equals 81. All right, so all that logarithm is really doing is just finding us what we would have to raise that base to get 81. All right, so log base 3 of 81 is just finding what we got to raise 3 to get 81. All right, let's go on to b. All right, so we're going to swirl this thing. All right, 4 to the 1st power equals 4. Well, duh, we know that. All right, but this logarithm is just saying what we need to raise 4 to get 4 is obviously just 1. Now let's interpret c. So we're not going to use the swirl method here. This is saying what do we need to raise 6 to get 1? Well, now we know anything raised to the 0th power is 1, and that's why we get 0. So this is just 6 to the 0th equals 1. Okay, so we can always phrase it in this type of question. 6 to what power equals 1? And maybe we can answer that question if we're familiar with our exponents. All right, now if we go down to d, okay, it's saying log base 1/2 of 4. All right, so what do we have to raise 1/2 to get 4? Now that's kind of tricky. I'm just going to rephrase it in terms of this question here. 1/2 to what power equals 4? So obviously we got to flip the fraction, so it's got to be a negative. And then we have to somehow change 2 to 4. Well, that would be done by squaring it. So our answer is -2. That's why we get that. All right, so 1/2 to the -2nd power. I'm going to put that in parentheses just to make sure you know that's that whole thing raised to the -2nd power equals 4. Awesome sauce. All right, now we got to go the other way too. So we got to be able to start in exponential form and rewrite it in logarithmic, because otherwise for some of these we're not going to be able to answer that question. All right, so let's go ahead and do so. Did I go too far? Nope, I didn't. All right. So we're going to rewrite the equation in logarithmic form starting in exponential form. Now, once again, if we're just trying this out for the first time, just swirl it, and after a while, maybe we'll get in the habit and maybe we'll start to understand what these things mean. Okay, so we're going to swirl it. Now, of course, if we're going to write it in logarithmic form, and by the way, just to pronounce this, it's just log and then rhythm. All right, logarithmic. All right, so if we're going to write this in logarithmic form, we need log there, okay? And then we're going to start with 2, and that's our base. Notice the base, how we write that base is it's a little bit below log. It's kind of like a subscript. And it's a little bit smaller, just like a subscript. All right, so log base 2 of 16 equals 4. All right, if we scroll down to b, once again, we could swirl it. All right, and that would be log base 7 of 1 equals 0. All right, so once again, our logarithm is just yielding that exponent, what we would have to raise that base to get whatever the argument is. All right, so we're going to go through these next two really quickly. This one might be hard to write down because we have 1/4 as our base. Just write it nice and small, make sure it's below log, and we're all good. And then 4 should be on basically the same level, as I like to call it. I'll just do this in yellow so it doesn't come over very strongly. So log and 4 are on the same level, equals -1. Once again, for the last one, we got log, and we could write this 10. I'm just going to write it once on the very first time. Log base 10 of 0.01 equals -2. Now, we talked about log base 10 being the common logarithm, so it's actually not necessary to write that base 10. We could write it as log of 0.01 equals -2, and what's implied as the base is 10. So if you ever don't see that base there, that little subscript looking thing, then know that this is just the common logarithm. It's log base 10. Okay, and the reason why it's the common logarithm is obviously a lot of things we talk about are in base 10. Okay, the whole mathematics that we do in this common era essentially is base 10 mathematics. Okay, we have tenths, hundredths, okay, the tens places, hundred places. We do base 10 mathematics, which actually wasn't always the most common thing. All right. Now, the next one, if I can get to it. So now we're going to evaluate the expression. Okay, rewriting it is necessary. That's our necessary skill to then go ahead and solve some of these questions. So in order to solve some of these questions, we have to be able to evaluate some of these logarithms. Okay, so remember, a log is just basically the inverse of an exponent. Okay, it undoes an exponent. Oops. So if we take a look at example 3, part A, it's asking us, what is log base 2 of 4? And maybe it might be necessary, at least in these introductory stages, to actually kind of swirl it. And to swirl it, we need an x there. We need something that we're looking for. All right, log base 2 of 4 equals what? All right, that's basically the question that we're asking ourselves. Now, if we want to swirl it, we'd have 2 to the x power equals 4. So in other words, we're trying to figure out 2 to what power equals 4. And in this case, that's pretty simple. So log base 2 of 4 is just 2, because 2 squared equals 4. All right, once again, if we take a look at B, we could just do the same thing, just to start out here. All right, we can swirl it. 3 to the x power equals 27. And now we're just asking ourselves, 3 to what power equals 27? And we talked about that in the very first introductory slide. So 3 to the third power equals 27. Now maybe we don't need to write it anymore. 4 to what power equals 64? Okay, that's that's the next question that we would ask. In that case, that would be 3, and we can just do some trial and error, whether on our calculator or not, to find that answer. All right, 6 to what power equals 6? Well, it's the same, so that would be 6 to the first power. 7 to what power equals 49? That would be 2. All right, and then finally, in this one, it says just log of 1,000. All right, of course, we could just type that into our calculator. It's got that log button. We could just type in log of 1,000, and we would find our answer. But remember, the implied base there is 10. So really what we're asking is 10 to what power equals 1,000? And that would be 3. If we would raise 10 to the third power, we would get 1,000. Also, on a quick side note, I'm going to use B as this example here. We could type this into the calculator as well, but we do have to change the form of it. All right, and this is something that we're going to discuss also in later sections, but I feel like it's useful to discuss now as well. So we can type this into the calculator by writing log of 27 divided by log of 3, just translating this into two independent common logarithms. So basically log of the argument divided by log of the base. And that would also be a way to get our 3. All right, but it is really useful to understand what these things mean. All right, so let's move on. We're getting there, folks. So far, we're just building up our skills to answer questions that we'll see in the future. All right, so in example 4, we're evaluating the expression, and in this case, we're going to get some different types of answers. We got all positive integers in example 4. That's not going to happen now. So if I want to rewrite this, and I'm going to rewrite this for every single one because I think it's useful. For part A, we could rewrite this as 4 to the x power, or 4 to what power equals 2. Huh. Well, we know 4 to the first power equals 4. To get a smaller number, I guess we could raise it to the 0th power, but 4 to the 0th power equals 1. So it's somewhere in between 0 and 1. All right, and maybe we remember this when we talked about quadratics, or maybe we will remember it when we were talking about squaring things and taking the square root. But if we took the square root of 4, we would get 2. And if we remember correctly, right, we had the index. When we're talking about the square root of 4, the index implied there is 2. And remember, we could rewrite this in exponential form as 4 to the 1/2 power. All right, so the answer to this question is we could raise this to the 1/2 power to get 2. Or in other words, we could take the square root. All right, same thing in the next one. If we took the square root of 16, we would get 4, so that would be like raising it to the 1/2 power. All right, so going all the way back to chapter 6 when we talked about these rules for exponents. All right, if we take a look at C, we're trying to figure out 4 to what power equals 1 over 16. All right, well, that means we would have to get this 4 to the other side of the fraction. We know what does that, negative exponents. Okay, and then we'd have to change the 4 into 16. Well, 4 squared would be 16. So our answer is -2. And then finally, we have 1/3. What would we have to raise that to get 9? And it would be the same thing. We would have to change what side of the fraction bar it's on, so that's a negative exponent, and then change that 3 into 9, so that would be squaring it. So we get -2. All right. All right, we've got a few more examples. So I'm just going to go through some of these really quickly. So hopefully we're getting the hang of this by now. All right, 3 to what power equals 9? That would be 2. 3 to what power equals 81? That would be 4. Okay, 2 to what power equals 8? That would be 3. And hopefully with enough repetition, okay, we're seeing the connection between these numbers, between 3 and 81, 3 and 9, 2 and 8. Now, 4 and 64. Okay, well, 4 to the 4th power, 4 to the 3rd power, would be 64. And then we'd have to change what side of the fraction bar it's on, so that would be a negative exponent. All right, same thing here. 6 to what power would be 1 over 216, or 1 on 216? That would be -3. 5 to what power would be 1? Just 0. All right, so obviously practice makes perfect. And now what we're doing is we're getting ready for some of these more complicated questions that we're going to have. Now before we get to that, we have to talk about inverse functions. So we've already talked about how logarithms and exponents are inverse functions. Okay, and when we talked about compositions of functions earlier on in the year, we talked about what it means to be an inverse function. All right, it means that g of f of x would yield x, okay, and f of g of x would yield x. All right, so in other words, if we put f of x into g, we would return the input value. Okay, if we put g of x into f, once again, we would return the input value. It would basically undo that whole equation and give us back what we plugged in originally. All right, and that's why it's an inverse function. All right, and that gives us something that we could use. All right, if we would put f of x into function g, that would give us log base b of b to the x power. And if that yields x, that means these things just undo each other. So if the base and the argument of that logarithm is the same, just cancels out. All right, that is just 1. All right, and the same thing is true for f of g of x. All right, let me do this in a different color here. F of g of x is taking g of x and plugging it into f. So if I take g of x here and plug it directly into f, that means replace that x with all of this. That would give us b to the power of log base b of x. And once again, we know that that just yields x. Okay, so that means that this basically undoes each other, and we just get 1. So that's just 1 times x or x. Awesome sauce. I know that might seem complicated, but in the next examples we're going to see it's pretty easy. So in example 5, evaluate the expression. So 10 to the power of a log of 6. All right, so if we're doing this, log of 6 implied there is a base of 10. So the base of the exponent and the base of the logarithm are exactly the same. Since the base of the exponent and the base of the logarithm are the same, this cancels out, and we just get 6. All right, note this is a little funky. That's supposed to be right there in this little gap here. In part C, this is supposed to be to the left there a little bit. I don't know why it looks like that. So in part B, this says 8 to the power of log base 8 of 12. All right, the base of the logarithm, base of the exponent is the same, so that's just 12. Same thing here. The base of the logarithm, base of the exponent is the same, so that's just 9. So that makes, if we know that that characteristic, that makes these pretty darn easy to do. All right, if we move on to the next ones, now it's in logarithmic form, so log base 2 of 8 to the x power. The logarithm and the exponent don't have the same base here, but we could rewrite one of these so that it does have the same base. Okay, with the skills that we have, we could change 8 and write it as 2 to some power. All right, so 2 to what power is 8? Well, that's just 3. Okay, so we could rewrite 8 as 2 to the 3rd power. So log base 2 of 2 to the 3rd power and really to the x power. Well, let's use some rules for exponents here to simplify this. So we have log base 2 of 2 to the 3x. All right, now we see the base of the logarithm and the base of the exponent is the same. So those cancel out, and we just get 3x. All right, so we simplified that using some of what we know about logarithms and about exponents. Part B, we have log base 5 of 25 to the x power, and 25 is just 5 squared, so we can rewrite that as log base 5 of 5 squared to the x power. Now this step is really unnecessary. Okay, we can rewrite this if we know our rules for exponents as 5 to the 2x power. And once again, we have 5 as the base of the logarithm, 5 as the base of the exponent, so we would just get 2x. And then finally for part C, ooh, this one's kind of tricky. 2 to what power is 64? All right, so that, let me not put x there because we already have x. 2 to what power is 64? That might be a tricky one. All right, so we're going to rewrite that. Maybe we know 2 to the third power is 8, like in the previous example. 2 to the fourth power would be 16. To the fifth would be 32. And then finally, to the sixth would be 64. All right, now I'm just gonna shortcut right to this last step, use our rule of exponents, and then simplify this. All right, log base 2 of 2 to the 6x would just be 6x. Awesome sauce. All right, so that's just our introduction into logarithms and exponents and evaluating logarithms and exponents by rewriting in logarithmic or exponential form. All right, folks, so that's it. So hit the like if you enjoyed that, subscribe, and like always, have a great day.